Hello students, now we'll move forward to the next concept, that is atmospheric pressure and the gauge pressure. In the last class, while studying the variation of pressure with depth, we have came across these two terms, that is atmospheric pressure and the gauge pressure. Now we will see how the atmospheric pressure is determined, or what are the instruments we are using for the atmospheric pressure calculation, and what is the gauge pressure. See, we know that the earth is surrounded by the gaseous envelope like air and other quantities like nitrogen, carbon, and etc. So the earth is surrounded by the gaseous envelope that is called as the atmosphere. Collectively, all the gases we are calling it as an atmosphere. The density of this atmosphere goes on decreasing as we go higher from the earth's surface. Means, while on the earth's surface the density of the atmosphere is higher, and when we go up from the earth's surface, that is when we go away from the earth's surface, the density goes on decreasing. So the atmospheric pressure, we will define it as the atmosphere or air exerts the pressure on the earth's surface. That pressure is known as a atmospheric pressure. Whatever the atmosphere or earth is giving the pressure on the earth's surface, that pressure is known as atmospheric pressure. And this atmospheric pressure is maximum at the surface of earth, and it decreases with increase in the height. As we move away from the earth's surface, the atmospheric pressure also decreases. And we have an instrument to calculate or to measure the atmospheric pressure. That instrument is known as barometer. And this barometer, first it was invented by the Italian scientist Torricelli, Evangelista Torricelli. And this barometer consists of a long glass tube. See, this long glass tube whose one end is closed and another one end is open, but it is filled with the mercury. In whole long glass tube, it is very thin, it is consists of a liquid mercury, and it is inverted. See, the closed end is at a upper side and at the lower side it is a open end. So it is filled with the mercury and it is inverted and kept in a mercury bath. It is a mercury bath. This tub is having the mercury only, so it is made inverted and it is placed in the mercury. Because it is having the mercury inside this tube, so this barometer is known as mercury barometer. See, the above this space above the mercury level in the tube has only mercury vapors. See, in this space it is a vacant space. At this space it is also known as a Torricelli's vacuum. At this space there is no any external pressure is there. Whatever it consists is only the mercury vapors. Because it is having the mercury, this gap, it is known as Torricelli's vacuum, and this gap, the pressure is only because of the mercury vapors, and those that is equal to very much less, so that is equal to 0, which is very much negligible. So at the point A, see this point A, at point A the pressure is only due to the mercury vapors. So at point A we are considering it as the 0. The pressure at the point A is as 0. So next comes the point B. This point B, it is same as the pressure at the point C. See here, there is a point C here, and we have a B point inside the tube. Inside the tube we are having the point B, and in this mercury bath we are taking a point C. Both B and C are having the same level, means both are at the same height. So both the points B and the C are having same atmospheric pressure. So the atmospheric pressure PA, we are defining it as PA is equal to rho GH, where rho is the density of the mercury, G is the acceleration due to gravity, and H is the height of the mercury column in the tube. This H. Whole the atmospheric pressure is known as PA is equal to rho GH. So, as we say that the atmospheric pressure is proportional to the height of the mercury column. See, by this equation, PA is equal to rho GH, where atmospheric pressure is proportional to the height of the mercury column. For this reason, the atmospheric pressure is expressed in terms of the height of the mercury column. That is, the normal or the standard atmospheric pressure is defined as, it is in terms of height of the mercury column. We will see that is the pressure exerted by the vertical column of 76 centimeter or 0.76 meter height of a mercury at 0 degree Celsius at sea level at a latitude of 45 degree. This is known as the standard atmospheric pressure. This is the definition of standard atmospheric pressure, which says that the pressure exerted by the vertical column of a 76 centimeter height of a mercury column at 0 degree Celsius at sea level at the latitude of 45 degree. And we know that the atmospheric pressure equation is PA is equal to rho GH. By this definition, we came to know that the height must be 76 centimeter and the acceleration due to gravity based on the sea level, that is 45 degree latitude, and whatever the density is there, that is in terms of, that is of the mercury, that is when it is of 0 degree Celsius. So we will have these three terms like rho, that is the mercury of the density of the mercury at 0 degree Celsius is 13,596 kg per meter cube, and at the sea level at 45 degree latitude the acceleration due to gravity, that will become 9.806 meter per second. And by using these two equations, and we know the height of the column, that is 0.76 meter, then substituting these all, we will get to know the standard atmospheric pressure. That is, then standard atmospheric pressure is equal to rho GH, and substituting these three terms, we will get the standard atmospheric pressure equal to 1.013 into 10 raised to 5 Newton per meter square. And in place of Newton per meter square, we can also write pascals. We know that the unit of pressure is Newton per meter square, or we can write Pascal. So that is in terms of Pascal, we can write that 1.013 into 10 raised to 5 pascals. But this atmospheric pressure is having certain units, like not only the Newton per meter square or a Pascal, it also has some other units, like the another unit for the atmospheric pressure is bar. That is, this bar is expressed as 1 bar is equal to 10 raised to 5 pascals. here in this equation we are having 1.013 into 10 raised to 5 pascals. So if we want to express it in the form of bar, so we can write it as 1 atmospheric is equal to 1.013 bar. That is, we know that 1 bar is equal to 10 raised to 5 pascals. Substituting this 10 raised to 5 in the form of bar, so we'll get to know 1 atmosphere is equal to 1.013 bar. This is the one form of unit of the pressure. And another unit of the atmospheric pressure is torr. Torr means this is the unit we came to know because of the scientist Torricelli, because this barometer is invented by the Torricelli, no? So that's why in honor for that scientist we have given another unit for the atmospheric pressure, that is torr, which is defined as 1 by 760th part of the standard atmospheric pressure, and that is 1 torr is equal to 1 mm of Hg. That means the pressure required for the increase of 1 mm height of the Hg column. In the vertical column in this barometer, to increase the 1 mm height of the mercury level, how much pressure is required? That is known as 1 torr. That is equal to 1 torr is equal to 1 mm of Hg. So the relation between 1 atmosphere is equal to 760th torr. That is, in the relation between torr and the pascal becomes 1 torr is equal to 133 pascal. And these are the sum of the units for the atmospheric pressure. We are not using these all the units. In some sectors these are used, like bars and millibars in the meteorology, torrs in the vacuum technology, and mm of Hg. This is used for the medicine, that is to calculate the blood pressures. They are using the units of mm of Hg, and torr it is also used in the physiology. This is about the atmospheric pressure. Now we'll see the another instrument, that is open tube manometer. This is the instrument which is used for the measuring of the pressure differences. See, here we are studying atmospheric pressure and also gauge pressure. Gauge pressure means this is the differences of the pressure between 2 points separated by the depth h, that is known as gauge pressure. So in gauge pressure we are mainly determining the differences in the pressures. So in open tube manometer, this is the instrument used for the determination of gauge pressure. So see, it is used for the measuring the differences, pressure differences. And see, in this diagram it consists of a U-tube. See, this is a U-tube which is having a suitable liquid in it. In this tube it consists of a suitable liquid. That is, suitable liquid means if we want to calculate the smaller pressure difference, then we will use the lower density liquids like oils. And if we want to calculate the large pressure differences, then that time we are using the higher density liquids like mercury. So we are using a suitable liquid in this, and its one end is open and another end is connected to the system whose pressure is to be measured. See, its one end is open and what another end of this U tube is connected to the system whose pressure is to be measured. This here in diagram, this is referred as a P. This is the system whose pressure we are going to measure. One end of this U tube is connected to this system. So next, see, pressure at the points A and B are same. See, this A point and B point are both at the same level, and we came to know earlier only in the hydrostatic paradox. That is, if the liquids are at the same level or same height, then both are having the same pressures at same time. So here the point A and the point B both are at the same level from the reference. So both points A and B are having the same pressure. So next we got to know the points pressure at point A and B. So next, by measuring the height of the liquid column, by this height of the liquid column H, we will get to know we can calculate by using H, we will calculate the gauge pressure difference, that is P minus PA is equal to rho GH, where P is the pressure at point A and B, which is same for the both A and B, and PA means the atmospheric pressure. How much pressure the atmosphere is acting on this open end, that is PA, that is atmospheric pressure, and H is the height of the liquid here, and the density rho is the density of the liquid whatever we are using in this, and G is the acceleration due to gravity. And this is about the open tube manometer, which is used for the measuring the pressure differences, mainly gauge pressures. And this is about the atmospheric pressure and the gauge pressure. Next, we have a streamline flow. What is mean by streamline flow means, just take example like when you start the water tap in your homes, when you start the water taps slowly, very slowly, just start that water tap, that time whatever the liquid outcome, whatever the water flowing from the tap is very slowly and very smoothly, where that is called as streamline flow. That is, when the water is coming from the tap is very slowly and very smoothly, there is no any disturbance in that flow. So that is known as streamline flow in generally. And when you increase the water flow, that time the water rushes and there is no any steady or a smooth flow of water. So that is not a streamline flow. Earlier, when the water is flowing very smoothly, that is known as streamline flow. We will see the definition of streamline flow. That is, when the flow of a liquid is such that the velocity v of every particle of the fluid at any point is constant, then that flow is said to be steady or a streamline flow. See, consider this diagram. In this diagram, there is a tube in which the liquid is flowing from the points A, B, C. We are considering in this tube, we are considering the points A, B, C. These are the 3 points where the velocities are V1, V2 and V3 respectively. Consider a flow of a liquid in the tube. In this tube we are taking a flow of a liquid, which is as shown in this figure. The path of the particles are represented by the line A, B, C. See, the streamline flow means when the particles coming from this tube, when they reach the point A, they will get the velocity v1, and when they come to the point B, they will have the velocity v2, and when they come to the point C, they will have the velocity v3. Then that flow is known as streamline flow. That is, let v1 is the velocity of the point A, v2 is the velocity of point B, v3 is the velocity of point C. If whatever the points or the particles coming to the point A, they will, if they have the velocity v1, and when that same particle comes to the point B, then they will have the velocity v2, and that same particle come to the point C, then that time it will get the velocity v3. Then that flow is known as streamline flow. That is not only for these three places. If at any point of that tube, the velocity of the particles crossing that point are having the constant velocity, then that flow is known as streamline flow. See, here we are considering the path of the particle is represented by the line ABC. The ABC is the path of the particle. Let v1, v2, v3 be the velocities of the particle. v1, v2, v3. These are the velocities of the particles at the position A, B, C. A, B, C. If all the particles coming or moving in the path A, B, C, whatever the number of particles may come, but that all the particles will have the, when they come to the point A, they must have the velocity v1, and when they move to the point B, they must have the velocity v2, and when they move further for the point C, they must have the velocity v3. Then that flow of the fluid is known as steady or a streamline flow. And the path followed by the particles of the fluid in that streamline flow, this path A, B, C, is known as streamline. And there are some characteristics for the streamline. That is, a tangent at a point on a streamline gives the direction of velocity of a fluid particle at that point. That means when we draw a tangent, see, when we draw a tangent for some points, then that tangents means that is a straight line which touches the curve at only one point. That is, see, these are the straight lines which are touching that path or a curved path only at one point. See, at point P, this is touching at only single point, and for Q also it is touching at single point. So that tangents, whatever we are drawing on that path, streamline, those are giving the direction of the velocity of the fluid particle. See, this is giving the right side direction, and it is also giving the direction of velocity at that point, and this is also giving the direction of velocity of the particle at a particular point, and this is the direction of velocity at a particular point Q. This is the one of the characteristic of a streamline. And next is, no two streamlines can cross each other. Means streamline flow means which is having a same direction and which is moving in a steadily or a smoothly. So if if we consider if two streamlines are crossing each other, if they intersect, then at the point of intersection, there will be two directions of motion, right? If we have a more than one direction of motions, then what happens? Then after that there will not be a steadily flowing motion of that particles or a fluids. So that's why the particles will have a more than two directions for motions, so which is not possible in case of a streamline flow. So that's why there is no two streamlines can cross each other. These are the characteristics of a streamline. Next we have a equation of continuity. Equation of continuity. Whatever the streamline flow we are calculating, that is the fluid dynamics. Before the streamline flow, whatever we have studied, that is the fluid statics, because in those cases whatever the fluid we have considered, that was in the rest position. But when we started learning the streamline flow, the fluid is not in the rest position, that is moving, right? So the study of fluid which is in the motion, that is known as fluid dynamics. So from the streamline flow we are studying the fluid dynamics. See, and in case of equation of continuity, while learning the equation of continuity, this is the equation. This equation of continuity expresses the law of conservation of mass in fluid dynamics, which gives the law of conservation of mass in the fluid dynamics. We will see that one. Consider a liquid flowing in a tube of a varying area of cross section. Consider a tube. See this tube which is varying in a area of cross section, means the point A is having some other cross sectional area value, and for point B it is having some other cross sectional area value. So let us consider at the point A, that is let A1 be the area of cross section, V1 be the velocity of the liquid. A1 is the cross sectional area at the point A, and V1 is the velocity of liquid. V1 is the velocity of liquid at the point A, and ρ1 be the density of liquid at the point A. At the point A, ρ1 be the density of the liquid. And while at the point B, A2 is the area of cross section, V2 is the velocity of the fluid, and ρ2 is the density of the fluid. That is at the point B. See. Next, consider at a point A, that is the distance travelled by the liquid at A in time delta t. Consider at the point A, the liquid, whatever the liquid flowing from that point A at the time of delta t. Then the distance travelled by the liquid, that is given by, that is distance is equal to V1 into delta t, because V1 is the velocity of the particle at the point A and delta t is the time, because we have the velocity is equal to distance divided by time equation. So by this equation, distance is equal to velocity into time we will get. So velocity into time. This is the distance travelled by the liquid at point A in the time delta t. Therefore, the mass of the liquid crossing the area A1 in the time delta t at a point A. At point A, the mass of the liquid, we know the liquid is moving, means the liquid is crossing the point A. So, when the liquid is crossing the point A, the mass of that liquid whatever has crossed with the area of A1, that is equal to, we know the density, so we will reform the density equation, that is we have the density is equal to mass divided by volume. So rearranging the in terms of mass, we will have delta m is equal to, that is delta m1 is equal to volume into density. And volume equation, volume is equal to, we have a1 v1 into delta t, because v1 delta t is the distance and a1 is the area into distance, we will get the volume. So substituting this in this equation, we will get delta m1 is equal to a1 v1 delta t into density rho 1. So by rearranging this equation, we will get the mass flux, that is delta m1 by delta t is equal to a1 v1 rho 1. Take it as a equation 1. And similarly, the mass of the liquid at point B, the mass flux of the liquid at the point B is delta m2 by delta t, that is equal to a2 v2 rho 2. Similarly, by the equation same as equation 1 only, then we will get the equation 2. Since there is no any liquid is leaving from the system or entering the system in the length of a to b, right? That is, there is no any liquid is leaving the system from a to b, there is no any liquid is going out of this length, and no any other liquids are coming into this length. So that's why the mass flux at point A will be equal to the mass flux at point B. Whatever the mass flux is there at point this A, that will be equal to the mass flux at the point B. So that's why we will write from equation 1 and 2, we will have A1 V1 rho 1 is equal to A2 V2 rho 2. Take it as a equation number 3. See, we know that the liquid is incompressible. Incompressible means while applying pressure, the volume of the liquid is not changing. So since the volume is not changing, so the density will be constant, or a density will be not changing. So we can write it as rho 1 equal to rho 2 equal to rho, or a constant quantity. So while substituting this rho in the above equation, we will get the equation 3 as a1 v1 is equal to a2 v2. So in generally, we can write it as av is equal to constant, that is because a1 v1 is equal to a2 v2 means the area of cross section and the velocity of the particles product at point A is equal to the product of area of cross section and the velocity of the particles at point B. So in generally, we can write the AV is equal to constant at every point of the pipe. This equation is known as the equation of continuity, and this states that as the area of cross section of the tube becomes larger, the velocity of the liquid or a fluid becomes smaller. While area increases, velocity decreases. As velocity increases, area increases. This is the statement of the equation of continuity. This is about the equation of continuity. Next we have the laminar flow. Laminar flow means if the fluid flows over a horizontal surface in the form of layers of a different velocities, then that type of flow of liquid is known as laminar flow. If the liquid, whatever it is flowing in a horizontal manner. See, this is the laminar flow diagram. The liquid is flowing in a horizontal manner, that too in the form of layers. It is having, this liquid is having a different layers of the liquid, and each liquid layer is moving with a different velocities, but no any layers are interacting with each other. Whatever the layers are there, they are going in a straight line with their path. They are not interacting with the besiding layers, other layers of the liquid. So that type of flow is known as laminar flow, and this is a kind of a streamline flow. It is a, in generally the laminar flow is a streamline flow. And the turbulent flow means the flow of a fluid in which the velocity of all the particles crossing a given point is not same. Means if we consider a single point of a fluid, and at that point all the particles which are crossing that point are not having the same velocity, means this is just the opposite of the streamline flow. While in the streamline flow, the whatever the flow was a smooth and regular, but in case of a turbulent flow, whatever the motion of fluid is there, that is irregular or a disorder. That is known as the turbulent flow. And this is the diagram of a turbulent flow. See, the layers of liquid are coming, and when they hit a object, then the direction of that flows of a liquid layers get changed. And that is known as a turbulent flow. In generally, see the example for the turbulent flow is while in a river, when the water is flowing in a smooth and steadily, that is known as a streamline flow. But when that streamline flow of the water gets hit to the some other stones or a hill, then that time the white colored water you will see, that is the disturbance happens in the flow of that fluid. That disturbance whatever that happens, that is the turbulent flow. In that turbulent flow motion, the directions of the particles will be different for a different particles, and this is about the turbulent flow.